So in section 12.9, I'm going to be looking at applying knowledge of the antiderivative. So first of all, let's look at this idea of finding the plus c, that constant that we keep on adding on whenever we're looking at the general antiderivative. Again, let's look at the ideas. F prime of x equals 2. F of x, the original function, is going to equal the antiderivative of 2 with respect to x. So I'm going to end up with 2x plus c. If I look at a family of rules that will work in this format, this linear format, then you can see I can come up with all of these. And they're all very different. So the c represents 3, 2, 1, 0, negative 1, negative 2. Same idea over here. If f prime of x is equal to x, then the original function is going to equal the antiderivative of x, which will end up a half x squared plus c. Again, you can see the family of these parabolas. And once more, you can see the c being represented by 3 on 2, 1, 0, negative 1, negative 3. So in order for us to work out exactly what that c is, we need some more information. We've got question 1 here. We need to work out what y is, given that the derivative equals 3x squared plus x plus 3. What we also know is that when x is equal to 1, y is equal to 0. So the point 1, 0 is on this curve here, y equaling. So we begin, y is equal to the antiderivative of, with respect to x. We start performing the antiderivative of 3x squared is 3x cubed on 3. The antiderivative of x is x squared on 2. Antiderivative of 3 is 3x. And we've also got this unknown constant. Tidying things up, you can see that y is equal to. But now we're going to make use of this fact. When x is 1, y is equal to 0. So I'm going to make y equaling 0. And I'm going to substitute x equaling 1 into the rule. Now what you'll be able to see is that the only thing unknown to us is this c. Further workings. And finally, you can understand that c is equal to negative 9 on 2. So that tells us that y is equal to x cubed plus a half x squared plus 3x minus 9 on 2. Usually, if we were told to work out what y is given the y dx is equal to this, we'd come up with that as our answer. Notice that we've got that general c. But now we're fortunate enough to come up with a specific antiderivative. Whilst this is a general antiderivative involving the c, this is a specific antiderivative. Of course, we can also do that on our CAS. I'm going to start by working out the antiderivative. So menu, calculus, integral. Don't worry about the terminals. And it's going to be of 3x squared plus x plus 3. And doing it with respect to x. So you can see that's what it's equal to. Just what I've got here, except for I haven't included the c. Next, I'm going to define an f of x function. So I'm going to go menu, actions and define. And I'm going to say that f of x is going to equal x to the power of 3 plus the fraction x squared on 2 plus 3x, and I'm going to add to it that unknown constant, so I'm going to call that c. Notice that with this term here, I could write it as x squared on 2, or I could just write it as a half x squared. So now it's defined. I want to solve for c. So I'm going to go menu, algebra, and solve. And I'm interested where f of 1 is equal to 0. So that's based on this fact here. We know that when x is equal to 1, y is equal to 0. So we've got f of x equaling 1 is going to equal 0, And instead of solving for x, which is what we usually do with our solve function, we're solving for c. So we're saying that in this equation here, x is equal to 1, and f of x itself, the y value, is equal to 0. Let's work out what c is. And we get that negative 9 on 2. So that is exactly the same. So obviously you can do it by hand, and you will be required to do it by hand, but it's very efficient to use our CAS as well. All right, so in problem 2, we need to find the equation of the curve of f of x, given that its derivative is equal to this, and that when we substitute 1 into the original f of x, we get a result of negative 5. We need to do it by hand and also using the CAS. So let's start that f of x is going to equal the antiderivative of this derivative here, this expression, with respect to x. I take the 8 to the front of the integrand, and now I'm looking at working out the antiderivative of this expression. So it's going to be 1 over the coefficient of x, and so the value in front of x is negative 2, so it's negative 2, being multiplied by the new power. The original power was negative 5, increase that by 1, it becomes negative 4. All of that is multiplied by the linear factor, so the 1 minus 2x, raised to the new power, so 1 more than negative 5. I'm going to add to it the constant. I'm calling this specific constant C1. And the reason I'm referring to it as C1 is because I've got this 8 out the front. So I don't want to just keep on using C all the way through, because the value of C actually changes in each line. So this is just some specific constant called C1. I'm now going to tidy things up. So I'm going to take the 8 through, and I end up with negative 2 times negative 4 is positive 8, and this 8 being multiplied through the top is positive 8 there. So I have 1 minus 2x to the power of negative 4, plus 8 lots of that specific C1. Now, we know that 8 lots of a specific constant C1 is just going to be a constant value, so now I can call it just generally C. And I've got 1 minus 2x to the power of negative 4 there. So this is what f of x is equal to. I'm now going to use the fact that 1 comma negative 5 is a point on f of x. I'm going to sub x equaling 1 into the rule, and I'm going to have f of x equaling negative 5. So that will leave me with the only thing unknown being c. And you can see my workings here. 1 take away 2 plus 1, it's going to be negative 1. All of that's raised to the power of negative 4. So that's 1 over negative 1 to the power of 4. Negative 1 raised to the power of 4 is just 1, so it's 1 on 1. So it's 1 plus c equaling negative 5. Take 1 from both sides, I can establish that c is equal to negative 6. So now what I can say is that f of x is equal to 1 minus 2x to the power of negative 4, taking away 6. So rather than just having the general constant, I have a specific constant, which is negative 6. And we're able to determine that it was negative 6 because of this fact here. Now just reorganising things a little bit, so rather than expressing it with a negative power, I'm going to bring it to the bottom, so 1 minus 2x to the power of positive 4, taking away 6. Now let's take a look at how we can find f of x on our CAS calculator. So I'm going to find the antiderivative of the derivative, and that will return us to the original function f of x. Menu, calculus, and then integral. And I don't need any terminals. I'm going to place the derivative in here, so 8, 1 minus 2x. And that's raised to the power of negative 5. And of course I'm doing that with respect to x. Whoops. Hit enter. So I now know that the original function f of x is going to equal this, plus some unknown constant c. So I'm just going to copy that. And now I'm going to define f of x. So I'm going to go menu, actions, define, and that f of x is going to equal, and just paste that, plus some unknown constant c. It's now defined. From the question, we know that the point 1, negative 5 is on f of x. So we're going to use that bit of information, x equaling 1, y equaling negative 5, to help us work out what c is. So now menu, algebra, solve. And I want f of 1 to equal negative 5. And I'm solving for c, the unknown constant. And you can see I produce negative 6, which is, of course, exactly the same as what we did by hand. Box just outlining all of the important parts of when we're applying antiderivatives. It's all fairly straightforward. Just remind you again about this situation here. Here we have a linear factor to the power of n. Then what our technique is to find the antiderivative is to simply take 1 over a, which is the coefficient of x of the linear factor, multiplied by the new power. Then we multiply all of that by the linear factor to the power of the new power, which is going to be 1 more than what it was previously, and then plus this unknown constant. Also, just a reminder that the antiderivative of dy dx, the derivative, is simply going to be equal to y plus c, where c is that unknown constant. Let's look at another application. Here, we need to find f of x. We know that the derivative is equal to 3 plus 4x minus x squared, and we know that 0, 4 is a point that lies on f of x. So f of x is going to equal the antiderivative of f prime of x with respect to x. So it's the antiderivative of this, and this will simplify to f of x equaling that line there. Notice I've got my plus c, the unknown constant. I need to solve for that. I'm now going to make use of this fact. F of x is equal to 7 when x is equal to 0. So f of 0 is 7, so we have the f of x equaling 7 here, and I'm going to substitute x equaling 0 for everything. And you can see that we end up with c equaling 7. So this line here is my general solution, or the general antiderivative of f of x. This is my specific antiderivative. I can only be specific when I know an extra bit of information. So without that fact, I can only produce that the antiderivative of f of x is this line. But with the fact, I'm now able to say specifically that the c is in fact 7. So in problem 4 here, we're dealing with a hot air balloon ride, or just a hot air balloon. We are told that the derivative is equal to 4t take 1. So change in height with respect to change in time is equal to 4t take 1, where h is the number of meters above ground we are, and t is time in seconds. In A, we need to write h as a function of t. So we have the derivative. To go backwards and get h, I need to work out the antiderivative of 4t take 1. So h is equal to the antiderivative of the derivative with respect to t. So it's the antiderivative of 4t take 1, and I end up with 2t squared take t plus an unknown constant c. Now, I'm going to use the fact that at the beginning of this balloon ride, time is 0, and the height that will be above the ground will also be 0. So here's my h function, including the unknown c. I'm going to set the height to equal 0, and I'm going to substitute that time is 0. And there you can see that I end up with a 0 for c. So this will all become 0 plus c. So this in fact should be c just here, not 0. So 0 equals c. That is that my h function is 2t squared minus t. B, find the height after 4 seconds. So now what I need to do is substitute t equaling 4 into the h function. So here's my height given by this rule here. Let's sub in t equaling 4, and you can see we produce 28 meters. C, how long does it take for the balloon to reach a height of 60 meters? So here's my h function. I simply make h equal to 60 and I solve for t. Now, of course, I could just use my CAS if it was a CAS-enabled question, but here's the approach if we're doing it by hand. I take 60 from both sides, and now it's in the format of a quadratic equation. In these workings here, I'm making use of the general formula for a quadratic equation. And you'll see that these are my two exact solutions. So approximately equal to 5.73 or negative 5.23. And of course, we dismiss the negative version. We accept only the positive version because we can't go backwards in time. So again, with these kind of application questions, you need to think about, do the answers I get, are they appropriate? Are they feasible? Are they realistic? And obviously that's silly, so you dismiss it. Here we are looking at straight line motion again. Remember that velocity is simply the derivative of displacement, and that acceleration is the derivative of velocity. So it makes sense that we can work backwards as well now that we can find the antiderivative. So displacement is going to be the antiderivative of the velocity function. And velocity is going to be the antiderivative of acceleration. Let's look at an application of this now. The acceleration of a particle travelling in a straight line is given by a of t equaling 2t. We need to find an expression for velocity if t equals 3 and v equals 0. So firstly, we're just going to find out the general solution for the velocity, and then we're going to work out from this information here specifically what the c is, that constant. So the velocity will equal the antiderivative of acceleration with respect to t, and we end up with t squared plus c. I'm now going to make use of this fact that after 3 seconds, the velocity will equal 0. So v of 3 equals 0, which will equal 3 squared plus c, so I've just sub that point in. And you can see we can establish here that c, the unknown constant, is negative 9. So now my velocity, v of t, is equal to t squared take 9. B, find an expression for the displacement. We know that the displacement is simply the antiderivative of velocity. So now I can take my found velocity rule and work out the antiderivative of that. So displacement is going to equal the antiderivative of velocity. So it's the antiderivative of t squared take 9. And here is my displacement rule, again with a c. I'm going to have time being 0 and my displacement being 0. So we are starting from the origin, and if we're starting from the origin, our displacement will be 0, and the beginning of time, of course, is also 0. So I'm making use of the point 0, 0 here. I sub in all of the values, and you can see that my constant is also 0. So my displacement function is x of t equaling 1/3 t cubed minus 9t. That gives me my displacement for any value in time. And as I said here, we start at the origin, time is 0, so therefore we are making use of the point 0, 0. So in question 6 here, or problem 6, we have the velocity of an object. It starts 3 meters to the right of the origin and is given by v of t equaling 12 minus 6t, where t is in seconds and v of t is in meters per second. And we are considering time being between 0 and 6. Okay, it's straight line motion, and we've got a reference here to right. So obviously the straight line is going left to right, not up and down. We need to work out when it stops. When is it that the object stops? We've been given a velocity rule. So obviously when an object is at rest or it is stopped, then the velocity of that object is 0. It's not moving. So for A, we want the velocity to equal 0. We solve for t, and we can see that it stops at 2 seconds. B, what is the displacement at any time? So for B here, what we're looking at, displacement is simply going to be the antiderivative of velocity. We know that from the yellow table that we presented earlier in the video. So x of t is equal to the antiderivative of velocity, and we end up with 12t minus 3t squared plus some unknown constant c. What I'm now going to do is sub in the point 0, 3. If I think about my displacement and the straight line motion moving left to right, my origin is at here, 0, and I'm 3 meters to the right. So I'm going to think that 3 meters to the right as being positive 3. Hence, I'm subbing in t equaling 0 and displacement equaling 3. If I do that, I can establish clearly that c is equal to 3. So my displacement function is 12t minus 3t squared plus 3. C. How far is it from the starting point when t equals 4? So now what I need to do is substitute time equaling 4 seconds into the found displacement function. So for C, I've got time equaling 4. I need to work out what the displacement is, and you can see it's 3. Now that is exactly the same as what it was at the beginning. So we've moved 0 meters away. Remember that this is our starting point, and then at the 4-second mark, I'm also there. Let's take a look at this graph here. This is my displacement running up and down and my time going on. So what I've just found out is that at time equaling 0, my displacement is 3. It's obviously going to be going up, and then at the 4-second mark, it's also 3. So it's returned back to that same displacement. On this graph, what would it look like? Well, I begin here at the 3. I've come up as high as a certain value, then came back and returned back to that 3. D. Where is the object when it stops? So what we need to do now is work out. So when the object is stopped, we want v of t equaling 0. Now from part A, we established that that occurs at the 2-second mark. So where is the object at the 2-second mark? Let's substitute that into the displacement. You can see it's 15 meters. i.e. we are 15 meters to the right of the origin. Again, taking a look at our graph here for our displacement, that means that at the very beginning, here at time equaling 0, I travel up, and then 2 seconds later, I'm going to be 15 meters away from the origin, and then I'm going to come back, and at the 4-second mark, I've returned to the starting point, 3 meters away from the origin. So that tells us where the object is when it stops. It's at the 15 meters to the right of the origin. E, how far does it travel in that first 4 seconds? Let's consider this graph. So here's time going by. We know at the very beginning we are 3 meters to the right. We also know at the 4 seconds mark we are back 3 meters to the right. We also know that at the 2-second mark, we are 15 meters to the right. So in the first 2 seconds, we travel a distance of 15 take away 3, 12 meters. In the next 2 seconds, we return back to that 3 meter mark. So therefore, we've also traveled an additional 12 meters. So in total, 24 meters.